Okay, hi everyone. Assalamualaikum. So today I would like to begin with the chapter number 3 for our subject, Multimedia Technology and Application. So from this particular class, basically I'll be talking about the multimedia data. Okay, so for this class will be part 1 of that of this particular multimedia data subtopic. Okay, for today I would like to talk about analog and discrete phenomena, and followed by image sound data represented as function and waveform. So then somehow we will talk about the sampling and analyzing, whereby this sampling is particularly quite important in the sense of talking about the segmentizing of time horizontal axis, while we will talk about the quantization afterwards, whereby this quantization is basically describing the discrete, try to discrete the idea of the y-axis. Okay, so the things happen in sampling will be talking about aliasing, whereby the aliasing is when a continuous signal has been digitized to the digital signal, and then will be transferred to A from A to B and back to B to A, right? So when B to A is sent back, so A couldn't play or reproduce back the originals data that has been sent A to B back to A to B, B to A. So that would be called aliasing. So meaning we cannot gain the original sound or data back again from digitalizing the continuous time signal. Okay, right. So that would be aliasing. So speaking of the quantization is basically talking about the y-axis. So we will find the way that to differentiate between how the level of quantization that we set and the error that has been calculated from both estimation and the real data. So that's what we call it SNR. So signal to noise ratio. So the fifthly is the data storage. So we will talk about how is and how large the audio files and the image file. When we talk about we do have several certain of specification given, so that would be the how we going to calculate the data storage. So last but not least would be talking about the bandwidth and data rates. So the bandwidth is the thing that related to how was the signal width during the selected frequency to be sent from A to B, while data rate is basically how the data has been sent from A to B based on bit in second. So yeah, that's the thing that we'll be talking about for today. So jumping to the first contents for today will be the analog and discrete phenomena. Okay, right. So the things that related to the analog and discrete phenomena before that, basically we should understand the things that related to what is the multimedia data is defined. So the multimedia system application have to deal with first thing first is how to generate the data itself from nothing, and if we got the data in our hands, so how we do manipulate the data. So means we change this the how to say the original of the shape of the data itself. For example, from analog to digital, for instance, right? So we try to manipulate them in order to get. Remember the one that we discussed about an apple. So apple is when we compress, then it shouldn't be like an apple, right? So that would be the things similar to the data. Example, we have something like this. So meaning this is a huge data consideration in our hands. So basically we want it to be like this, like small. We need to compress them. Okay, storage of data, meaning we try to put our data in certain kind of storage, and later after store and sending from A to B, but later on we will talk about how to present the data at the receiver sides. Okay, so then by completing all the four the types of data implementation at the top one, so basically we try to focus on how to communicate, how to communication, what is the things that happen in behind the data in terms of communication or information that has been sent to A to B. Okay, so a majority of the data is large, and then the difference of data may be need to synchronize. So this is happening when we talk about, let's say, as simple as a video, or even a YouTube, or even a TikTok, or even Instagram kind of clip video. So basically, in that particular video need to be sent from A to B uh, in two things, right? So one is the movement of the frame regards to movie. Okay. So the other thing is what is the happening when we talk about the sound basically convey with the clips has been sent to A to B. So that would be synchronization between movement and audio. So that would be things related to the temporal relationship. Meaning, temporal meaning that speaking of the frame. So basically, when I talk A, B, C, so A is basically T equals 0, B T equal 1, while C T equal 2. So meaning the time 0, A has been pronounced by me. When T equal 1 is B is pronounced by me, and C, and etc. So that would be temporal relationship between the integral properties. So meaning by time domain. Okay. Okay. Speaking of static and continuous media data. Okay. So right. So some of the media that we discussed so far, we have 5 media element, right? So I think you guys remember things related to the 5. Okay. So two of them is basically the one that we discussed in this particular topic will be sound and images. Okay. So related to the static. Static mean not changeable. Okay, kind of the data is not really kind of changing itself. So in other way that example we say hello world. So hello world is not changing any because the string of HELLO until D at the world side. So meaning we have a specific string of data. So normal data could be data, text. Okay. So the other thing is speaking of, we have an image of our beloved Melaka tree. Okay, example. So the image of the Melaka tree is basically a single images contributing a static data has been given to us, like the pixel 700 times 700. That's it is. So not changing any. Graphics is emoticon, emoji, and etc. So speaking of the continuous data media, so we have time dependent media. So I did talk about just now temporal relationship between the multimedia. So the time dependent data whereby we talk about media, animation, and audio as example. So for example, audio. So when I say saya hendak makan, meaning the audio means are reflecting to the my voice from the throat to the mic, and reproducing the intersection between my air molecule with the air molecule in this room, right? So that would be collusion between that molecule. So that would be changing by time saya nak makan, kind of. Okay. Animation the same. Animation is when we talk about the movement of the things, and the video obviously the movement of the video, kind of. Okay. Analog and digital signal. So speaking of the analog that has continuous nature rather than pulse of discrete nature. So continuous nature meaning, okay, sorry for the things that I don't have any tools to write over here. So continuous meaning, so just imagine that we have x-axis and y-axis. So the continuous mean the graph is continuing producing the amplitude on the y-axis value, right? So without stop. So that would be continuous. So for this continuous data, normally they will be related to electrical physical analogies, meaning temperature, voltage, frequencies, phases, and so on and so forth. Okay, so the advantages of the analog signal is has a potential in infinite resolution of the signal. Okay, so what is the resolution? So resolution does mean high resolution. Remember, so when we talk about resolution, it does mean that how the details of x-axis of one particular data. So for example, if we do have x-axis in 4 value compared to 8 value of x-axis, clearly the 8 value will be reproducing a good data for us. For example, an image. So image 4 by 4 is not clearly compared to 64 times 64, right? Because the limitation of the color intensity and the edge. Okay. So obviously the in continuous or in analog signal, it will be high density because temperature, for example, in digital we do have timing like segregation of time. So 1 p.m. to 24, but in continuous analog time, so 1 p.m. to 24 minutes and how many second and how many detic that we said. So that would be continuous high resolution signal. So processing, it might be simple because when we do have the x-axis, we might have the amplitude value, right? So speaking of disadvantage of analog signal, noise obviously regards to the random variation. So this random variation is commonly occur even though we are using the same point A to B with the same A to B facilities, and the distribution of the noise production is really happen there when we are talking about the analog signal, because it might be happen when the how to say the data could be sent from A to B depending on the time, depending on the regional, like sending from the west to the east coast. It could be happen because of the quality of the connection wired and so on and so forth. So that would be normal for the random vibration. So impossible to recover the noise distortion. So meaning to say that it will be difficult kind of to make things back, because um, it is not completely changeable or intermediate change compared to the digital, because digital, when we talk about digital continuous to digital, we change the continuous to digital discretely from 0, 1, 2, 3, 4. We put it block by block, right? Okay, so digital signal is represented by sequence. Okay, meaning I said just now block by block. So example, temperature. So temperature is rising up from morning to the noon, right? So and then going down from noon to the dawn. Okay, so that would be the things that related to going up to going down. So but the thing is, when we talk about digital, so the going up to going down, the value of the temperature is basically going up and down discretely. So meaning it's not curving down, but it is shown as a number. Example, 25 degree, 24.3 degree, 23.9 degree kind of things. So that would be a sequence of number. Okay. Advantages of the digital signal opposed to analog signal: the degradation of the signal noise cannot be only detected but corrected as well. So that would be easy to correct it, because since we have the point of the sampling things from continuous to digital one. Scale well with increased complexity of system, so whereby we can have the optimized things in our data when we manipulate the sampling rate and sampling data. Okay. Disadvantage of this digital signal is obviously the error prone. So because of we try since we manipulate the sampling, exactly when we talk about sampling, meaning we cut the continuous data at specific areas. So meaning between that one cut data and the other one cut data has been deleted. So only the representative of data, example t equal 1 and t equal 2, right? So t equal 1.1 to 1.9 is gone. So that would be error prone. Has lower resolution than analog signal, obviously, because we talked about just now, because we sample it down for by the time frame second, right? So obviously there will be lower resolution than continuous, because the continuous happen to take all everything in the hand of data. Okay, right. So analog and digital signal conversion. So the world we send is fully of analog signal. Yeah, analog or continuous signal must be converted to digital for computer processing. Obviously here, since all the electronics and computer devices that we use right now, including tab, computer, laptop, iPad, cell phone, list down. So basically, it processes everything in digital world. Okay, so in order to to utilize all the devices, basically we need to change. Example, as I talk right now in continuous, in analog. So this voice has been going into the laptop and changing from analog to digital by ADC converter, right? So that would be the thing. So digital and discrete signal are signal that computer can really deal with. So as I mentioned earlier, every single thing that we have used and utilized right now is everything in digital. So we cannot run away from that rules. Okay. Okay, this is the example as I mentioned earlier, ADC, analog and digital signal converter. So normally this is happening before the data has been going into the devices. Okay, as we talk, so the voices coming from our throat is analog. So will be converted with the sound card at that particular devices, changing our voice to 0, 1, 0, 1, 0, 0, 0, 1, 1, things like that. Okay. Okay. When our voice is to be heard, or is to be presented, or is to be heard again, so basically that 0, 1, 1, 0, 0, 0, 1, 1 will be converted again by DAC, digital to analog signal. So because from that particular specific binary number converted to DAC, so then that specific number will be turned back to the saya suka makan. Okay, in analog world. So means that what we say just now. Okay, so that would be the thing. Okay, right. So analog to digital signal conversion, converting a continuous analog to discrete digital signal has two subprocess. Okay, so this is the main or core things to be happen in converting to A to D, analog to discrete. Okay, so digital. Sorry. So there are two. So one is sampling. So conversion of continuous space or time. So remember, the keyword here is continuous space and time. So time, remember x and y. So x will be time. Time is t. So when we talk about x, t is sampling. So whereby we sample everything in the horizontal axis. So either the space for the horizontal axis is 0 to 1 is 1, or 0 to 2 is 2. So depending on how the sampling that we chose to be in sampling rate, right? Okay, quantization is converting continuous value. Okay, remember value. Signal that has continuous range or of intensity or color into discrete. So whereby intensity mean or amplitude means, so when we talk about x is time, y is amplitude, intensity, or any number reflecting to the amplitude of that particular x. Okay, so that would be quantization. So the same way with the sampling happen in x, while quantization happen at y-axis. Okay, from continuous time signal to digital time signal, the same. Okay. Okay, two primary media in digital media are images and sound. As I mentioned earlier, So in this particular subtopic, we will talk about two, images and sound, obviously. Okay, in the sense that two are combined to produce a video. So that would be one thing I mentioned earlier. So because a video is basically a combination of images frame moving plus the audio. Okay, can represent it as a function, and we can realize this function by means of corresponding graph. So we can portray them, we can illustrate them, we can represent them in a particular graph. Okay, so whereby it could be one-dimensional function and two-dimensional function. It depends on the condition. Like example, for sound, it is one-dimensional function whereby the x is time while the y is amplitude of that particular sound. Okay, so if we think of the sound as a continuous phenomena, so we can model it as a continuous function of x. X meaning or t in time, so y is the amplitude. Okay, y. So whereby we can say over here is air pressure amplitude. Okay, later we talk about that. Okay, so the essential form for function representing sound is sinusoidal, so the shape of sine wave. So normally the sine wave has been used. It's not cos because frankly speaking, the sound is started from the 0 point, so not the 1, because cos is coming from 1 to down, while sine is 0 to 1, right? So that would be reason why sine is considering the priority for the sound representation data. Okay. All right. So this is the sound. Is a mechanical wave, which means that it's result from the motion of particle through a transmission medium. Okay. So just now I mentioned about when we say something from our throat. So basically our voice is going out of our mouth, and then the air is going out from our throat. So this particular air is basically occluded with the air which happened to be already in the air. Okay, so the molecule. So the occlusion happened to be producing the pressure. So meaning the more that the air is occluding the molecule, existing molecule air from the throat to the air, so we this produce an area of a high pressure in this range of air. Okay, so then what we have sinusoidal of the peak one at the top and the down one at the bottom, meaning less occluded sound. Okay, from our voice to the air. So that would be producing sine wave. Okay, so we can take a look over here. A signal frequency 440 hertz tone with no overtone represent as a form. So whereby C, not C is down on the left top, and then not G is on the right top, and not E is the left bottom, and combinational of C, E, G is the bottom, left bottom, right bottom, sorry. Okay, so that just now is talk about the sound representation. So now is image representation. So similar to the sound, so basically when we talk about the image happen to be related with intensity, we may also use the sine wave to portray our color intensity at that particular region of pixel. Let's say x times y. Okay, so meaning so this is x, guys. This is y, right? So x 1 to 5 is 0, so meaning 0 area. So 5 to 10 is black, right? So we could see this phenomena as a waveform. Let's say we see it from this from the horizontal axis. So we might see in intensity in through this one. So imagine that we see from the bottom. So we could see that the white one is basically this. The black one is this, and white is this, black is this from the bottom. Okay, then this particular bottom is happen to be this one, and this is x-axis for the location of that particular things. Okay, so then considering x and y of the axis that in one images, we could say that vertical pixel positioning and horizontal pixel positioning, whereby we could say that two-dimensional pixel positioning for the color intensity rather than one amplitude in sound data just now. Okay, so that what we call it two-dimensional. Okay, so in sound, one-dimensional. So that would be the things. Okay, so now we talk about sampling rate and aliasing. So as mentioned earlier, sampling is happen to be in x-axis, right? Okay. So sampling is very crucial in order to change the continuous data file to digital data file. Okay, whereby we the sampling is make the the data to be discrete point at which measure of the continuous phenomenon. So whereby the sampling is changing the continuous to this discrete. Okay. Okay. So in image, the sample point are evenly separated in space. So imagine that the image we have vertical and horizontal, right? So in that particular horizontal and vertical is basically separated by spaces, so meaning pixel by pixel, whereby sound are eventually separate by time. So remember, sound is one-dimensional value, so meaning x is time, y is amplitude, right? So that would be the thing. Okay. The number of sample taken per unit time or per unit space is called sampling rate. Okay, whereby either we talk about images and sound, both we will have the sampling, okay, number of sampling. So whereby the sampling, the sample taken per unit time, example, 1 second, or per unit space, example, 1 pixel, is to be sampling rate, guys. Or we can say that resolution. So that's the reason why we can see that we can hear and see the things that are related to the images has been called as high resolution image quality, right? So that would be the things. So the terms has been used for sampling. Okay, apart from that, quantization. Each sample could be represented in a fixed number of bytes called sample size. Okay, so now I would like you to take note over here. Okay, in sampling, we have sampling rate. Okay, while the quantization is not quantization rate. So we have sample size. I hope that you guys can remember it. Or we can call it bit depth. So the reason that we call it bit depth, it does mean that how the bit has been restricted to be digitized in the amplitude axis. So that would be bit depth. So imagine this is y-axis, the depth of the y-axis. So whereby we call it bit depth. Okay, so sampling rate, number of sample taken of the signal in the given time using 1 second. So that would be sampling rate happen for x-axis. While bit depth, or what they call it sample size, okay, remember, interchangeable, sample size or bit depth, when the sampling resolution or with, okay, the more bit, the better quality of the audio. Okay, so meaning for the y-axis, so how many choices that we have by differentiating the bits. Okay, say that we have 2 bits data, right, in y-axis. So 2 bits data meaning 2 power 2 means 4. We have only 4 value to describe our data for amplitude. So meaning 2 over 2 meaning 0, 0, 0, 1, 1, 0, 1, 1, right? Okay. So imagine that we have 3 bit data. So 3 bit data, 2 power 3 means 8, right? So 0, 0, 0 until 1, 1, 1. So that will be 3 bit data. So when we talk about 8 bit data, we have 0, 0, 0, 0, 0, 0 until 1, 1, 1, 1, 1, 1, 1, 1, right? So when we talk about 16-bit data representation, we have 4 times quadruple 0 to 4 times quadruple 1. So imagine that we have many choices of y-axis representation segmentation. Tinggi. So that would be the thing. Okay, now sampling rate and aliasing. So this is focusing on the sampling rate where we talk about x-axis. Okay, aliasing is an effect that causes different signal to become indistinguishable when sampled. Okay, remember continuous data need to be sampled before it change to digital. Okay, so because the digital will be sent in computer, right? Okay, so when we have the digital data back, we will transform it to continuous back. So aliasing happen when the data has been digitized and sampled and sent and received back. So we translate from digital to analog. So we couldn't get the desired data that we have been digitized before. So that would be aliasing. So meaning the things that we receive is not the same what we supposed to be received. So that would be aliasing. So it is referred to the distortion or artifact that result when the signal restructured from sample is different, okay, than the original signal. So that would be the description of aliasing. Okay, so to guarantee accurate restructuring of the sample, right, we must use the sampling rate that is greater than twice, okay, the frequency of highest. So meaning sampling rate need to be greater than twice of frequency highest. So example, Fs smaller, equal or larger than 2 F max. So what we say, okay? Because sampling rate is a frequency, while the highest frequency is frequency 2, right? Okay. Example, we have sampling rate as 4,000. Okay. So what will be the highest frequency? So the highest frequency should be 4,000, right? It's because 2,000, 1,000, sorry. So because example, sampling rate is 4,000. So highest could be 2,000 because the left could be the same or higher than twice time. Okay. Okay, then we talk about Nyquist frequency. So Nyquist frequency is the highest actual frequency component that can be sampled. Highest, okay, frequency component that will be sampled by given without aliasing. Okay, without aliasing. Highest actual frequency component. Right. Half of the given sampling rate. Okay, now the keyword here is the Nyquist frequency is half. Okay, as mentioned earlier, Fs equal or higher than Fmax. So now Nyquist frequency is half than frequency sampling, right? So Fs over 2. So that what we call it Nyquist frequency. So Nyquist frequency, in other words, is respect to the highest actual frequency, right? Okay. So for example, sampling at rate 8,000, then Nyquist frequency is, okay, what is the answer, guys? Okay, here the Nyquist frequency said half of the given sample rate. So meaning half of the given sample rate is, okay, you tell me, what is the half of this number? So that will be the answer, right? Okay, so not to mention limited only in sound, but it will happen in image as well, okay? So image sampling and aliasing. So whereby the image also could be aliasing when we disable and couldn't manage to get a good sampling of choosing this sampling in terms of pixel, right? So okay, take a look at the left and right top one. So basically those are the good sampling because it could reproduce black white equally, okay? 4 to the black, 1 to the black. but this one slightly could be okay, but this one, okay. So if this sample will be here, that will be okay, but this is reflected to a bad sampling, guys. Okay, meaning undersampling and result in an image that does not match with the original. It may blur somehow, and it will be a false pattern. Okay, so imagine that you wanted to send a good image showing that a ball, so meaning the ball is kind of aging, okay, ages, akan berlekuk at the curve. So that would be the thing. Okay, so talking about the sound sampling and aliasing. Okay, this is the one of the example harmonics. Okay, in that particular sampling and aliasing in sound, we talk about harmonic. Harmonic are series of signal whose frequency are integer multiple of the frequency of the fundamental. Okay, whereby this is fundamental one. So this is the multiple integer multiple of frequency fundamental, right? So this is 1, this is half. Okay, meaning 2 lah. So that would be this plus this, we can equal this. While this one is 3. Okay, third harmonies. So meaning this plus this equal this. So until 2, 3, 4, 5 harmonic. Okay, right. So Nyquist rate, the lowest sampling rate that will permit accurate reconstruction of analog digital signal. Okay, Nyquist rate is twice of frequency of the highest frequency component in the signal being sampled. Okay, if you wanted to sample an audio wave that has a frequency component of 10,000 hertz, what is the sampling rate, guys? What is the sampling rate? So this is a clue from this slide, 19. So I guess you can get the idea. Okay, so from that particular discussion, so we might bring to the simplified version of the specific discussion has been done before. So we have two now. So whereby the first one is Nyquist rate. Okay, so the Nyquist rate is in frequency, obviously, in hertz. Okay, Nyquist rate is F and R equal to F max. So 2F max meaning highest frequency twice. Okay, when we talk about Nyquist frequency, we will talk about F and F equal 1/2 F sample. Okay, so that will be a relation between two. So finding Nyquist rate or finding Nyquist frequency. Okay, now frequency theorem for band limited signal. Okay, this will be considered when we have two kinds of the limit of the frequency. So one is the lower one is the upper one. So meaning we might subtract the upper to the lower and times 2. So that would be known as band limited Nyquist theorem 1. Okay. Okay. Audio aliasing. When the digitized sound is played, the frequency from the original sound will be translated to a different frequency. So that will be aliasing. So that digital sound doesn't sound exactly like original. So this is the phenomenon describing aliasing, guys. Aliasing. Okay. So the reason is too low sampling range. Example, frequency maximum is 5,000. Okay. What is the frequency sampling rate? Okay, 5,000 frequency max, meaning 2 times 5,000 is 10,000, right? So the sampling rate, it must be at least 10K. Okay, so imagine that we are giving the sampling rate as 8K or 7K. So too low sampling rate result in aliasing that aren't enough sample point for which to accurately interpolate the sinusoidal form of the original wave. So basically, the point from the sampling couldn't plotted again back in order to reproduce the original. So that would be reason at the back the original sound is not generated. So that would be audio aliasing. So take more than 2 samples per cycle on one analog wave, then the wave can be precisely reconstructed from the sample. So that would be kind of hint, a simple things to be said, right? Okay, so this is the example so far. The signal is 6337, which 637 cycle per second. So whereby so you might count this frequency by, you just pull, for example, this one. Okay, this one is 5 approximate, so this one is 3, right? So you can count how many cycle, okay, in 1 second. So this is millisecond, right? So this is 25 millisecond times 10 to the power of minus 3, right? So just imagine that we have 637 cycle in 1 second. So that would be signal given. So what is the sampling frequency, guys, over here? Okay. So signal is 637. It could be twice of that one. So could be 1274. Right. Okay, if we have exactly 2 samples per cycle, mention take more than 2 sample. Take more than 2 sample. Right. More than. So meaning 3, right? So this one is 3. So this one is 2. Okay. Meaning this one, 1 cycle. Okay. 2 sample per cycle, and the sample are taken at precisely maximum, this one, and minimum at the sine wave. Once again, the digitized wave can be constructed, yes, obviously, but the sample are taken at location other than peak and throw. The frequency may be correct, but amplitude is incorrect. Okay, whereby the frequency of that particular note, the point is correct, but the amplitude might not be correct. So that would be reason why at least 3, not 2. Okay. So this is the things that are reflected to 2 sample, okay, per cycle. So imagine this one is 2, this one is 2. Skip over some cycle. So imagine that we have this is okay still, but this component has been skipped, guys. So making it appear that frequency of the actual is lower than its reality. Okay, so the keyword, making it appear that frequency of the actual wave is lower than the real. Okay, so that would be makes Alice at 363. So sorry, happen also in this here too, and this. Okay, so we have not enough sample size in order to reflect it back our original sounds. Okay. Okay, this is exercise. What is the cost of analyzing in those digital media? So it would be good idea to solve by your own, right? Okay. So based on my video recording just now. Okay. What is the answer? Fs at least and larger than 2 Fmax, right? So that you may want to digitalize record a sound that has a highest 650 Hz. According to the Nike's theorem, what sampling rate should you have to use so that you don't get the sound aliasing? So yeah, 2 Fmax. I think you know the answer. And followed by number 3, right? Okay, now quantization. So the quantization is different than the things that are related to sampling just now, because sampling is considered the x-axis, while quantization is considered the y-axis, guys. Okay, right. Okay, quantization talk about the y-axis. So how we digital the amplitude axis. Okay, so in digital image, each pixel sample, what we say. Okay, because remember the in image we don't call it sample, we call it pixel by pixel. Reference a color as intensity at the discrete point of two different two-dimensional images, either x and y. So how many colors can we probably represent in the digital images, right? So determined by the number of bits used in represent each of the sample, the sample size of bit depth. Okay, so let n be the number of bits used to quantize a digital sample. Then maximum number of different value that can represented m is m equal n square. N. Okay. Okay, right. N is bit, guys. So meaning if 3 bit meaning how many? 8. Okay. So if 2 bits meaning 4. So 1 bit meaning 2. So what is the number? So for 1 bit, so 2 power 1 is 2. So what is the different number for 2 bit? 0 and 1. Okay. So what number for 2 bit? N equal 2 for 4 bit. Meaning we have 2 bit, 4 number, 0, 0, 0, 1, 1, 0, 1, 1, right? So that would be bit number. Okay. So if 1 bit is used per sample, only 2 colors are possible, black and white. So for example, 1 bit is 2 power 1, meaning 2 lah, M. So M is 2, either 0 and 1. So that would be the things. Okay. Okay, so different quantization, speaking of the difference value in the definition above the correspond color level or sound amplitude. So over here, color level is speaking about the images and sound amplitude is speaking about the sound, audio files. Okay, so we can classify this thing into 2 categories. So one is images and one is sounds. Okay, so at the left hand side, we have image. When we talk about 2-bit binary, so because 2-bit is considered ring 0 and 1, so white and black. So 8-bit meaning 2 power 8, 256. So we have 256 of color intensity on our hands. Okay, while 2 power of 224, obviously we have more. Okay, so in y-axis, obviously in sound we have stereo. Okay, I think you guys know about stereo and mono channel. Stereo means 2 channels and mono means 1 channel because we have left and right. Okay, yes. So 16-bit per sample for each channel. For 2 channel meaning 16 times 2, 30-bit per channel for y-axis for the sound. Okay. Okay, this sample size, or later on we call it bit size or bit depth, how precisely the value of the sample can be represented in y-axis. That will be quantization, guys. Okay, so in order to evaluate the quantization, so basically there will be a study known as quantization error analysis. Okay, so the sample must be round to the closest discrete label. So the quantization is, okay, take a look. Example, this is the blue. Dot is the original point of the original point of the data that we have. So the red one is basically the nearest quantization level for this blue one. So meaning the original dot over here couldn't be going to up to here because too far, right? So this one is the nearest one. So they put it this way for this level. So for this kind of level, blue, instead of going up, they will be going down because nearer again. Okay. So blue, red, blue, red. Here also, the blue is here and the nearest level to this blue is upper. Okay. So the quantization value means the difference between red and blue for each of the taken sample. So that would be quantization error. Okay. So you have, this one is, okay, I think this one is okay for that. Okay. So in order to make things happen, to analyze the quantization error, we call it signal to quantization error, SQ&R. Okay, so with n bits for quantization, the samples value range from -2n - 1 power to 2n - 1 power -1. Okay, right. So this particularly when we, for example, when we say that we have n equal 3, for example, right? Okay, let's do together. Minus 2, 3 minus 1. Okay, minus 2, 3 minus 1 meaning minus 2 power 2 kan? Okay, so meaning minus 4. So minus 4 to, okay, 2n minus 1. 2n minus 1 means 2 and 3 tolak 1, 2 power 2. 2 power 2, 4. So 4 minus 1 is 3. So meaning, for this particular 3-bit number, so from minus 4 to 3. So meaning, the quantization happen from minus 4, minus 3, minus 2, minus 1, 0. 1, 2, 3. So 3 to minus 4 happen to have 8 choices of number. So because 2 power 3 means 8, kan? Okay. So the maximum value, sample value is 4. Okay. On the scale of some value, the maximum quantization error is half of quantization. Okay. So the SQNR over here is 20 log 10 maximum quantization value over maximum quantization error. Okay, equal 20 log 10 2n minus 1 over half. Okay, so we can simplify this equation by putting the 2 over here to be upstairs. So then 2n and 2 minus 1 is 1 over 2, right? So 1 over 2 and 2 is cancel. So what we have is 20 log 10 to n. So this is this basically signal to quantization error, guys. Okay. SQNR. Okay, speaking about the dynamic range give us a measure of the range of the amplitude that can be captured relative to the loss of fidelity compared to original sound. So I think dynamic is talk about highest and lowest, frankly speaking, in our daily life. So yeah, in digital image, ratio of the largest amplitude color and the smallest. So meaning ratio meaning amplitude, largest amplitude with the smallest amplitude. Okay, in color, image. While in audio, different from the loudest and the softest. So that will be dynamic range. Okay. So this is dynamic range in terms of images. So we have the same range for 3 bits images. Okay, dynamic range in audio. So let n be bit depth. Okay, bit depth, remember, sample size. Sample size, bit depth, and bit size, meaning y-axis, are respected to the quantization things. Okay, the dynamic range of the audio file is d in decibel. So remember, here is in decibel, not in uh, any units. Okay, so d is equal 20 n log to n. So assumed to be nearer to 6n. So for example, 16 digital audio file has dynamic range of 6n. So meaning 16 times 6. And 8 meaning 6 times 8. Right? So that would be the dynamic range of audio. Okay, now we can simplify that the things that has been covered so far, the sampling rate and the bit depth. Okay, bit depth. Okay, sampling rate speaking about the x-axis, and bit depth is speaking about y-axis. Okay, because related to quantization in bracket. So there we go. And needed for creating a new digital audio files. Okay, so this is the sample of audio sampling rate so far that we have. 8,000 for hertz for mono means our used telephone, the desktop telephone is 8,000 hertz. And the CD quality sound is 44,100 hertz, alias 44.1 kilohertz. Okay, so two channel for stereo, left and right, with 16 bit per channel. So two channel, 32 bits. That we talk about in audio tape, 48 kilohertz. Sampling rate for 96 to 192 for DVD, 20 bit per channel. So meaning 48. It's quite big for DVD. Okay. Okay, now this is the example for data storage that we have in our hands. Okay. Right. The example is taken by having, let's say we have a digital file size, okay, without any compression in our hands. 1024 times, meaning 1024 times 768 pixel, because image, height and width. Okay, about the total pixel. So total pixel meaning width, the height time width. Okay, 1022 times 768 pixel. So we have 786,432 pixel. Okay, so this is pixel, one pixel, tiny. Color mode. What is color mode? Talking about color mode, color intensity, because of the color mode is RGB, guys. RGB is stand for red, green, and blue. Okay, right. So the pixel, one pixel basically have the intensity of RGB. Okay, independently 3 times. Okay, meaning okay, meaning we should have the three bytes over here. So because one R is 8 bit, okay? So G is 8 bit, so meaning bit per pixel is 24. So we calculate the 786 432 with 24. We have 18,874,360 68 bits now. Okay, so this is in bits, guys. In order to get bytes, okay, remember 1 bytes equal to 8 bits. Okay, so this number will be divided by 8. We have 2,359,296 bytes. So this in bytes. Okay, after we divide by 8 from bit to bytes. Okay, so okay, now speaking of data storage, that would be using this this B, capital B, guys, byte. Okay, so the byte is 2 million. So remember, in order to get mega, so the mega is 2 to 20 power. So mega is 1,048,576 byte. So this number will be divided by this, will having 2.25 megabytes. So that will be the size of one images with the size of 1024 times 768 pixel height and width. So 2.25 megabyte. Okay, so that would be the size of data storage. So now shall we go to the sound? Okay, this is the audio files that we have. Okay, let's say this file is not having any compression. Okay, so we have the specification given to us as 44.1 kilohertz, and the bit depth is 32 channels, since we have 16 for each. So we have 32. Say that the audio file is 1 minute, so meaning 60 seconds. We require to calculate it. Okay, right. Okay, for this reason, at the first time, at first we need to have 44,100 sampling rate times 32. Okay, so then we again times 60. Okay, because of second. 1 minute is 60 seconds. So 44,100 times 32 times 60. So we have 84,672,000 bits. Okay, now we got bits. Okay, so to have bytes, we need to divide this number with 8. So we have this. Okay, we have 10,584,000 bytes. Okay, so for the size, basically this number will be divided by this, guys. So because 1 mega, right? So then we have 10.09 mega. Okay, now In order to differentiate between file size and data rate, okay, so this one quite be tricky at some points. Since we require to have to analyze the size and data bits, so the size obviously in B byte, so but the data rate is in small b bytes, okay, bits, sorry, okay. So the bit is taken from here, 84, sorry, 84,772,000. So will be divided by 60 because second over here. Divide by 60. So then we have 1,411,200. Okay. Sorry. Okay. So then that what we have in 1 second for bits. Okay. So but here is megabits, right? So mega means we need to divide by 1048576 in order to have 1.35 megabits per second. So that would be the things related to this. Okay. So I think that would be same to the video itself. So video is 270 720 times 480. Okay, times that times 30 times 60 over here. So we have 14,929,000,000, 14,929,922,000 bits, right? So that way images required in bits. So remember, video is combination of images and sound. Sound is 84 million. So this will be combined together. We get this 15 billion. So in order to get bytes, so we divide this by 8. So we have this bytes, right? Okay. So this byte divide by giga. So giga is from here. Giga is 10732741,824 bytes. So we have 1.7 giga. Okay. So for this reason, just divide this by second at first, by 60, and divide by mega. So we have 238.65 megabits per second. Okay, this is the example for the storage. We have CD, DVD, memory sticks, HD, DVD, Blu-ray, and flash drive. Okay. Okay. So let's jump to the bandwidth and data rate. So I think this will be the kind of, hold on, things related to bandwidth a bit. Okay. Introduction to the bandwidth. Sound and video are time-based media that require large amount of data. So both capturing and transmitting sound and video in real time. Okay, right. So issues of bandwidth and data rate. Okay, so data rate has been discussed before in this slide. So we have 238.65 megabits per second. So that would be data rate. How the data has been sent from A to B, right? Okay, so bandwidth is the things differently. Okay, so this is the example at the beginning. Transmission of the discrete 0 and 1. So discrete pulses, discrete. Okay. So the question with regards to the bandwidth in this context, how fast can the signal be changed? V to a voltage of minus V back again. Okay. So the baseband transmission system with a bandwidth of 5,000 hertz. Okay, 5,000 hertz meaning 5,000 hertz meaning hertz is 1 over t, right? So in 1 second, 1 over 5,000. Okay, this one, 1 over 5,000 of 1 second system can be communicated of two things. If one voltage represents 0, another is 1, then the system can transmit 0 and 1 for every of second. So this means that it can transmit per second. Okay. Okay, now every 1 of 5,000 can send to 0 and 1 at say at 1 second. So meaning if we consider that 10,000 meaning 10,000 bit is because of 5,000 times of transmission of 201, meaning 10,000 bits per second required, right? So in other way, to turn it back in bits, okay? So because this is 1 bit, this is 1 bit, right? So 2 bits can 2 bits times 5,000, meaning 10,000 bits every second has been transmitted. So assume that the signal is sent to two possible signal as the previous example. So 0 and 1. So meaning the data rate is D in bit per second is 2 times B. So what is B? B is this one, 0 and 2. So meaning, sorry, B is hertz. Hertz is 5,000. So B is 2. So meaning 2 times 5,000 is 10,000 lah. Okay. Instead of having 1. Okay. So that would be this. If we allow that the more than 2 signal, so meaning we have 4 or 6 or 8, so multi-level meaning. So this D equal to B is differently. So 2B log 2K. So this K is basically example 4 possible signal. So meaning 2B 2 times 5,000 log 2, 4. Okay, so that would be data rates for that particular example. Okay, this one is the frequency range of particular frequency with, okay, so I think the width is basically difference between max and min. Okay, so that would be the idea of the width of signal. Okay, so when data is communicated across the airwave, it is sent along some particular channel. Width is band of frequency. Okay, for example, the range of the frequency allocated to a band constitute the bandwidth of the channel. Okay, the range of frequency. So, example, AM radio station, so that we have. So I think FM is commonly used right now. AM is commonly used in the climate change and disaster, right? This one. Band of 10K. So FM radio station is 200K hertz. Analog television is 6 megahertz. And HDTV is 20 megahertz bandwidth. Okay. So bandwidth is measured by cycle per second. Okay. So then the data rate is basically bits per second, guys. So that would be the things differently between the bandwidth and data rate or bit rate. So if measured in bit per second, there will be data rate or synonym as bit rate. Okay. So recall again when we talk about more than 2 bits that we have. Example just now, this one. Okay. So then we should know that the Shannon theorem C equal B log 2 1 plus S over P, whereby the S is signal power and P is the noise. Okay, right. So this is the data transfer for common communication line. So far we have telephone modem, ISDN. So this is the data rate, guys. It's not the bandwidth. Okay. Okay, this is also data rate taken for example, this one is gigabit internet. Lately, we are using this one. Okay, for LAN and so on. Okay, right. Okay, speaking of the audio data size, we might also discuss. I think this one will be covered on the next chapter, data 4, about the mu law. Okay, or A law in Europe. So that will be commonly we'll discuss soon. So how do we calculate uncompressed data rate based on the given sample rate, quantization rate, message size, and monostereo? Okay, take a look at here. We have sample rate 8 and bit per sample, right? Okay. So the data rate is commonly taken from here. Sorry. Okay. So telephone is 8, AM radio is 11, FM radio is 88.2, and etc. Right? So this one is, I think this one has been discussed before, and this one is kind of exercise to, as for you, if in case that you have time, then please do it. Okay. So I think that's all for this video. The part 2 will be coming soon. Hopefully, you will get something from the multimedia data from this chapter. Okay, thank you. See you again. Bye. Okay, thank you guys for watching NMZH channel. Hopefully you can get knowledge and benefit from the videos. Thank you so much. Assalamualaikum.